Welcome. Today we will look at the estimation of the fugacity coefficient using easy to measure variables. This will be the last aspect that we look at in this particular module on pure components. We have already seen what a fugacity coefficient is. While going through this, we will again take a look at what it is and refresh ourselves, refresh our memories with what the fugacity coefficient is. Now, first to arrive at the experimental conditions needed to estimate the fugacity coefficient, we are going to begin with the definition itself, the definition of the chemical potential, which we had given in the previous module. If you remember, this was equation 216. We will mention this once again. Dou Gt dou Ni at constant Tp and all other j's different from I, all other nj's different from Ni. This was defined as the chemical potential when we first introduced, or when we first strengthened the idea of the chemical potential. This was equation 216 way back in the previous module. Again, to emphasize, this was only one of the ways that we used to introduce the concept of chemical potential in the way we had organized our material. The chemical potential itself is a very powerful concept, and the interpretation of the concept of the chemical potential and its applications are definitely not limited to the definition or the first level interpretation that one gets from this definition. For example, by realizing that Gt is the total free energy of the closed system, the chemical potential of a component of a phase can be interpreted also as the amount by which the capacity of the phase for doing work other than expansion work is increased per unit amount of the same species added, assuming an infinitesimal addition at the constant temperature and pressure. This is this comes from whatever we have seen earlier, dou Gt dou Ni at constant Tp Nj was given as a chemical potential. Now, we are looking at Gt as the free energy apart from, or the capacity to do work apart from PV work, and then we said that this is the amount by which it increases when you infinitesimally add one of the species at constant temperature, pressure, and all other species remaining constant. That is one of the ways to interpret it. It is good to know this. Let us look at it again from this background. By realizing that Gt is free energy, the chemical potential of a component of a phase can be interpreted as the amount by which the capacity of the phase for doing work is increased, or the work itself is other than expansion work is increased per unit amount of the same species added, assuming an infinitesimal addition at constant temperature and pressure. And of course, as we have already seen, chemical potential is a valid concept for pure components also, although it was introduced using a multi-component system. Now, let us consider a pure component, which means there is no I involved anymore. It is just one component there, and therefore variation in I need not be considered in the equations that we wrote earlier. And for such a pure substance, dou Gt by dou N at constant T and P would become the chemical potential of that substance. Let us call this equation 351a, and we need to be clear here that chemical potential is a function of temperature and pressure too. It is just that it is being held constant here, and we are defining it as the chemical potential. We said we are considering only a pure component. Now, let us further restrict ourselves to 1 mole of that pure component. please pay some attention to this. This is where we are equating Gibbs free energy and chemical potential under these conditions. So, it is good to pay some attention to this. 1 mole of the pure substance, for that Gt, which is the Gibbs free energy of the closed system, would become equal to the molar value G, and from the definition dou Gt dou Ni being equal to mu, you can actually say that this is equal to mu under the conditions that we are considering. Now, using equation 2.8, which is for a closed system, we had written dg equals minus s dt plus v dp. Using this, we can actually write this in terms of mu. Therefore, d mu equals minus s dt plus v dp. Let us call this equation 352. Under the above conditions, dou mu by dou p at constant t is nothing but v, because see d mu is the total differential. This is again an exact differential in a state variable. D mu is dou mu dou t at constant p dt, and dou mu dou p at constant t dp. Considering this term alone, we can write dou mu dou p at constant t equals the v that is given here. V is easily measurable, so we will just look at that. Since we have a constant T here, let us impose the conditions of constant temperature. Let us also remind ourselves that we are trying to get at a means of estimating the fugacity coefficient. For that, we have started out with the chemical potential, and we are getting there slowly. So, let us impose the conditions of constant temperature, since we have a T constant here, and once we do that, pressure becomes the only independent variable. We initially said we have constrained it to 1 mole of a pure substance already, and the only variables that we are concerned with now were the temperature and pressure, and now that we have also kept the temperature constant, pressure becomes the only variable. If you have a single variable system, you do not have to look at partial derivatives anymore. They all become total derivatives, because the variation is only with respect to one variable, and therefore, the partial derivatives can be replaced by the total derivative. Therefore, we can write d mu dp equals v, and therefore, d mu equals v dp. Equation 353. Now, from the definition of fugacity, which is equation 3.1b earlier in this module, at constant temperature we can write d mu equals RT d ln f. This comes directly from the definition of the fugacity itself. This is equation 354. If you have some level of confusion, just go ahead and look back at equation 3.1b. This will become very clear. Now, in this equation we have d mu equals p dp, equation 353, and in equation 354 we have d mu equals RT d ln f, and they are the same quantities on the left hand side. So, let us equate the right hand sides. If we do that, equating the right hand sides of equations 353 and 354, the previous two equations, we get RT d ln f equals v dp. Now, let us do some manipulations. Note that we are getting to the fugacity coefficient. So, we will have to arrive at that in some way, and to do that, let us subtract RT d ln p, RT d ln p from both sides of the above equation. The thinking is something like this. We know that fugacity coefficient is f by p. So, somehow we need to get that into this kind of an expression. So, if we subtract RT d ln p from both sides of the above equation, we can write this as RT d ln f minus RT d ln p. The ln of A minus ln of B is ln of A by B, and therefore, we can write this as RT d ln f by p, and the right hand side of course is V d p minus RT d ln p. Now, d ln p is nothing but 1 by p dp, and therefore, V d p minus RT, which is already here, by p dp, which can, if you take dp out common, we can write V minus RT by p dp. Therefore, d ln f by p equals V by RT minus 1 by p dp. The need for writing it this way will become very clear. We are trying to bring it in terms of the compressibility factor. We know that PV by RT is the compressibility factor. Okay, we will get to that in a little while. Before that, let us integrate the above expression from p equals 0 to p equals some finite value p1, and if we do that, the integral of d ln f by p is nothing but ln f by p, and the upper limit at p equals p1 minus ln f by p at the lower limit p equals 0, which equals right hand side integral of 0 to p1 V by RT minus 1 by p dp. Now, let us recall the definition of the fugacity itself. This is again from equation 3.1b. The if you look at the definition of fugacity, it will say that f tends to p as p tends to 0, or f by p tends to 1 as p tends to 0, and note that this is nothing but the evaluation of ln of f by p at p going to 0 or p being equal to 0. In such a case, you have a ln 1 here, which is nothing but 0, and therefore, the second term on the left hand side of the previous equation is 0, and f by p is the fugacity coefficient at point 1 in this case, and therefore, ln of phi 1 or phi 1, here we have evaluated f by p, which is phi at p equals p1, and therefore, we will call it ln of phi 1, and ln of phi 1 equals the right hand side, which is integral of 0 to p1 V by RT minus 1 by p dp. Let us call this equation 355. We are almost there. In terms of the compressibility factor, because we have so many methods for compressibility factor, now let us try to express this also in terms of the compressibility factor. We know that PV by RT is a compressibility factor. We can write ln of phi 1 as integral of 0 to p1. This is z by p, this is 1 by p, therefore, this becomes z minus 1 by p dp. Let us call this equation 356. Let us take a look at this equation. Ln of phi 1 equals integral of 0 to p1 z minus 1 by p dp. We have on the right hand side all that can be evaluated. We already know methods for evaluating the compressibility factor, starting right from the initial part of this module, and therefore, by evaluating this, we can get an estimate of the fugacity coefficient at a particular point. In this case, 1 denotes the particular point at which the estimation is made. Okay, let us same thing, the methods used to evaluate the compressibility factors under appropriate conditions can be used to evaluate the fugacity coefficient. So, whatever information that we have gathered so far in terms of evaluating z, estimating z, can directly be ported on here to evaluate the fugacity coefficient. To appreciate this a lot better, let us work out an example. This is example 3.5. Let me first read out the example, evaluate the efficacy coefficient for our popular model system isopropanol under the conditions given in example 3.4, the same temperature, the same pressure, I think it is 200 degrees C and 10 bar, which is given in 3.4. What I would like to tell you first is that this problem is not trivial, although it is just one line there, evaluate the efficacy coefficient for isopropanol. That is because on the basis of whatever we have seen so far, whatever we have learned so far, the skills that are required to arrive at an acceptable solution to this problem calls for are slightly higher level skills. It requires some integration also. So what I will do is give you a lot of time to do this. Take about 5 minutes to think about this. The first hint is very clear, you will need to use the expression for the efficacy coefficient of course, but may not be very directly. So take about 5 minutes, think about this, and then I will give you some hints and lead you through the solution process. This is not as straightforward as the solutions that we have seen so far. Go ahead please, 5 minutes. Okay, now that you have taken the time to think through this, you would have connected some expressions for the efficacy coefficient, the one that we just saw, ln of phi1 equals 0 to p1 z minus 1 by p dp and so on. Maybe we will have to use that, but I already warned you not very directly. So let me start giving you some hints. The first hint is, try to express that equation 356 that we just saw, the expression for ln of phi1 in terms of reduced properties, Tr, Pr and so on, because if you do that, then the data, the amount of data that is needed significantly goes down, because in terms of reduced variables, those are applicable for a wide variety of substances, pure substances, and therefore try to express this in terms of reduced properties. Go ahead, take about 10 minutes and try to express the equation in terms of reduced properties, and then I will give you the second hint. 10 minutes please. Probably you are ready for the second hint now. We will see the solution when we work out the complete details, but let me give you a hint so that you can start thinking in that direction and pick up such skills which require thinking in one angle and thinking in another angle, putting them together for the purpose at hand. The hint is something like this: we have tables for reduced properties in the appendices. Express the equation for the fugacity coefficient in terms of those reduced properties. This is a very big hint. Okay, so go ahead 10 minutes and see how you can express the equation for the fugacity coefficient, which has already been converted to a reduced property form, in terms of these reduced properties, the values of which are available in the appendices. Let me probably give you a third hint now, it might help you. Those reduced properties are SR 0 by R, SR 1 by R, HR 0 by RTC, HR 1 by RTC. We have already seen that these are available in the tables of your appendix. So take about 15 minutes and link this up in terms of the expression for the fugacity coefficient in terms of these reduced properties to these reduced properties. Take 15 minutes to do it. Go ahead please. Okay, some of you would have arrived at the solution, which is very good. Let us look at the way of going about the solution. We have already seen from equation 356, the first step was to express this in terms of reduced properties. We already know that ln of phi1 is an integral from 0 to p1 z minus 1 by p dp, this we already know. Now the way to express this in terms of reduced properties is to replace these actual variables in terms of the reduced variables. We know that p is pcpr and dp, as we have already seen, is pc, which is a constant, times dpr. Yeah, okay, I have written down the steps here, pcpr and d of pcpr, and the pc, when it comes out common here, it will get cancelled with this. And now since pc is a constant and the variable of integration is pr, the limit of integration should also be in terms of pr. This that makes sense because you have this in terms of dpr. If we do that, it goes from 0 to pr1, ln of phi1 becomes integral of 0 to pr1 z minus 1 by pr dpr. It's quite straightforward and no major complications in converting this expression from the actual quantities to reduced variables. Now by transposing equation 349 below, think of the second hint that was given, try to express it in terms of the other reduced properties SR and HR and so on. The 349 equation is given here for a quick reference. 349 was SR by R equals minus TR, P reference to PR2 integrated, dou Z dou TR at constant PR by PR dPR, minus integral of PR reference to PR2 Z minus 1 by PR dPR, and this can be written as integral of Z minus 1 by PR dPR, which is this, equals SR by R plus TR into integral of P0 to PR2 or 0 to PR2 dou Z dou TR at constant PR dPR by PR. This was actually our Fugacity coefficient expression that we had gotten earlier for in terms of our reduced quantities. So we have this in terms of SR and something else here. Now if we can take care of this, then we have a means of calculating our Fugacity coefficient. Now what is this? To get at this, let us look at 348, which has again been given here for convenience. If you recall 348, you can go back and take a look at that. That will be HR by RTC equals minus TR squared integral PR reference to PR2 dou Z dou TR at constant PR into 1 by PR dPR. Therefore, this integral here, which is somewhat this here, can be written as minus, here take a look at this here, this is TR squared, here you have a TR, and therefore minus 1 by TR into HR by RTC becomes this integral that we are looking for, and therefore the Fugacity coefficient estimation integral of 0 to PR1 Z minus 1 by PR dPR becomes SR by R minus, this term has become 1 by TR HR by RTC. Now the RHS can be written as, this is where the link between what is available to us, we have values available in terms of SR0, SR1, HR0, HR1. Therefore, we need to relate whatever we have in terms of SR and HR to these. That was here, you have your SR by R minus 1 by TR HR by RTC. We link it up to whatever is available. We can write that as SR 0 by R plus omega times SR 1 by R is nothing but SR by R minus 1 by TR HR 0 by RTC plus omega times HR 1 by RTC. The one within this flower bracket is nothing but HR by RTC. Now, we can take these values from the tables available in the appendix. These are appendices or tables E5, E6, E9 and E10 of appendix E from your textbook Smith, Vannes and Abbott. This is pretty much similar to what we did in example 3.4, and substituting these values we get SR 0 by R was 0.179 and so on, omega is 0.665, SR 1 by R was minus 0.254. We have already seen this in the previous example, and 1 by TR minus 1 by TR is minus 1 by 0.931. This term HR 0 by RTC was minus 0.246 plus omega times HR 1 by RTC minus 0.265. This turns out to be 0.1053. What was on the left hand side was ln of phi1, and therefore phi1, which is the Fick coefficient at 1, is the exponential of 0.1053, which turns out to be 1.111. So, we have kind of integrated whatever we knew in terms of whatever was available and got an estimate of the Fick coefficient. If you want, you can go through the solution again to see the various ways in which we went about doing it, and in the next class we will do a review of whatever we have done in this module before we go on to the next module. See you then.